see here. Here we go. Okay, last time we were talking about conservative vector fields. Where we started was with the fundamental theorem of line integrals, right? And so, shockingly similar to the fundamental theorem of calculus. Almost kind of a rip-off of the fundamental theorem of calculus. Real quick thought, there's a point of view that says that all of the big, depending on how you define big, many of the big theorems that we're going to talk about in chapters 6 and 7 are in fact rip-offs of the fundamental theorem of calculus. This one's just a little bit more obvious about it. Right? Anyway, okay, so we talked about what it means, and we talked about why it works. And again, my favorite point of view is that what we are doing is looking at an accumulating quantity. Right? Once you realize that you have an accumulating quantity, I know I've said this a million times, it's just so important to what I think is the best way to think about this stuff. When you have an accumulating quantity, it behaves kind of like a stuff in a manner of speaking, and you can talk about its associated density, and you can compute it, therefore, by integrating that density. And taking that point of view, we gave a motivation for the theorem that change f of b minus f of a is, as it turns out in this case, a vector line integral of the gradient of the function whose change you're interested in. Okay. All right, so let's make use of this. The way we make use of this is actually kind of backwards. Think of this less as, here's something I want to compute, and I'm going to compute it by using a vector line integral. In practice, the way we tend to use this theorem is, hey, here's something I want to compute. And here's a handy-dandy formula for how I'm going to do so. Okay. All right, so here we go. Let me get into full screen mode. There we go. Let's compute this vector line integral. Now, I've pointed things like this out in the past, and let me do so again just to remind you. Notice this question does not announce itself as being, hey, you should use the fundamental theorem of line integrals. Right? It just says compute this vector line integral. This could be a chapter 5 problem. Right? On an exam, it's going to be, part of your job on an exam is going to be look at a question like this. It says compute this thing and decide which of several techniques might you use to compute it. Now, in this case, parametrizing what's already pre-parameterized, it's almost suggesting by the existence of that parameterization that maybe we ought to pull back through the parameterization. And if you did, it wouldn't be that bad. It's not the best way to do the problem, but it's doable that way. Now, we have another method for computing vector line integrals in some cases. Green's theorem. Right? So we could, just at a quick glance, it's not immediately clear that this is not a Green's theorem problem. There are some line integrals that are. In this case, I claim that Green's theorem doesn't apply, and we'll see why in just a minute. For the moment, let me just leave that dangling. What I'm going to do for this problem is I'm going to use the fundamental theorem of line integrals. Reminder, let's go back up to this original statement of it. If you're going to use the fundamental theorem of line integrals to compute a line integral, the integrand has to be a gradient of something. Right? It says so right there. And furthermore, that thing that it's a gradient of, we're going to need to know what that is, because that's the thing we'll be plugging into. Right? Is everybody on board? Okay. All right. So, here we go. Our vector field, this vector field right here, I claim is a gradient of something. Now, how did I know that? Right? What about this announces itself as being a gradient? There's nothing in the statement of the question that says that this is a gradient. How did I know? Before I pulled a rabbit out of a hat and found that this is the function, right, whose gradient is that. You can check the algebra, right? But how did I know in advance? We'll talk about that later today. For the moment, I'm just going to observe that, in fact, check it out, this is a gradient. Now, related question, where did the rabbit come from? How did I identify what this function is? That's another thing that we'll talk about, hopefully later today. We'll see how time goes. But if not today, then Wednesday. So, very soon. Okay, so again, we need to have that anti-gradient. Remember the anti-gradient, that's the thing that we're going to plug into. That's this little f function that we'd be plugging into. But now that I've identified that my integrand is in fact a gradient, I can cite the fundamental theorem of line integrals. Now I just need to know the starting point and the ending point. Notice that we start the way this curve happens to have been presented to us. Right? There's millions of ways that you can define a curve, right? But this one is given to us parameterized, and I can plug in the starting value of t, right, to find my starting point A, and I can plug in the ending value of t to get my ending point B. And it's just plugging and chugging. Right? F of B minus F of A, just using the fundamental theorem of line integrals. And poof, we're done. Everybody see how that worked? Couple of big looming questions. How did I know that was a gradient? Second looming question, where did the anti-gradient come from? How did I specifically find the anti-gradient? Again, coming. Okay. Pause for questions. Pretty good so far. Okay, awesome little theorem. Big theorem. This is a big theorem. Okay, next topic. We're going to talk about something called path independence. This is a very weird topic. I'm going to start off by making what I'm going to call a pretty, dare I call it, obvious statement. If you're looking at a line integral, it depends. The value of that line integral depends on what curve you're integrating over. Well, yeah, right? Of course it does. Here, I'll come back to what we just did up there, but let me just emphasize the obvious. Of course it depends on what curve we pick. Let's look at this example here. Here's a vector field, and this is what it looks like. About like this. Make sure you can do that, of course, right? Chapter 3, question. Look at a formula, draw the corresponding picture in reasonable cases. And I'm going to make the statement that various parts of these two curves that we're looking at, f.dr is clearly 0. Now, here's how I know. Let's see here. Let me change my mind and use blue for the vector field. Along in here, the vector field itself is 0. And if the vector field itself is 0, then f.dr is 0. You could imagine little dr vectors along in here. And of course, f.dr is 0. So I get no contribution to line integral there. Now, just for comparison purposes, let's see here. What about along this top edge? Well, here the vector field is that way, but my dr is that way. So even though f and dr are both non-zero, it remains. That dot product is 0 all the way along that edge. And likewise, all the way along that edge. So we're not picking up any line integral on 3 of those 4 edges, but then you notice that on this right edge, the vector field and the dr are both pointing the same direction. They're non-zero and they're pointing the same direction. And so we're going to be picking up positive amounts of line integral all the way along that right side piece of curve there. And with that in mind, if we look at our 2 different curves here, we have this curve C1. Well, that integral is clearly 0. There's no line integral anywhere along that. At no point along that curve is the fluid flowing along the curve. Not even a little bit. Whereas on this curve, we clearly get a positive line integral. So what an anticlimactic example. Of course the curve matters. If the curve didn't matter, we wouldn't write it down, right? It's the silliest observation ever. Okay, so that's what makes this statement here that we kind of glossed over real quick a moment ago. Outrageous. There are some vector fields where in some sense the curve doesn't matter. Only the endpoints matter. And which path you take, whether I get from 0, 0 to 1, 1 by the C1 curve or by the C2 curve, whatever, doesn't make any difference. What an outrageous suggestion that the path wouldn't matter. But this does happen sometimes, and in a certain sense of the word, kind of often. So such a vector field is called a path-independent vector field. There is this other terminology that the book likes, path-independent line integrals. I'm very uncomfortable with that terminology. Very importantly, this feature that we're describing is a property of the vector field. It's not a property of an integral. It's a property of the vector field itself. So grammatically, just to keep it clear, I like to use this term that we talk about vector fields as being path independent. All right. And it means exactly what it says. It means that if you have one of these special vector fields, and if you're interested in these two different line integrals, now it's got to be two different curves that share the same starting point and the same ending point. So that is important. They do have to start and end at the same place. But that said, a path-independent vector field will have the green line integral equal to the blue line integral for any two curves that start and end at the same points. Outrageous! Right? I mean, again, certainly not for this vector field. Major swing and a miss. Obviously, it matters. C1 and C2 are perfectly clear. Casual inspection is going to give you different answers. Okay, so let me try to persuade you that such vector fields do exist. And in fact, there's a bunch of them. And in fact, once I show you this entire category of vector fields that have this property, it's going to be one of those things where in retrospect it's like, well, yeah, actually that is kind of clear. And it's gradient fields. All have this. Regularity concerns, I'm going to say continuous gradient fields, but practical purposes, how we're going to encounter them, gradient fields. So now, again, very important. It does matter that the curves both start at the same point, and it does matter that the curves both end at the same point. But that said, if our vector field is a gradient, well, let me not circle that just yet. If it's a gradient, I claim that this green line integral over C1 and this blue line integral over C2, I claim are going to have to give us the same value. And again, it doesn't seem reasonable. How can I possibly expect that? Look at these. They're totally different curves, right? C1, all the points on C1 where I'm looking at the vector field and the DR, etc. None of those points are involved with the points where I'm going to be evaluating along C2, except that starting point, ending point, practically nothing. What seems outrageous? Here's why it works, and it's an immediate consequence of the fundamental theorem of line integrals. Let's look at the green integral. The green integral says I want to do a vector line integral of f. Oh, wait a minute. That means I'm doing a vector line integral of a gradient. Fundamental theorem of line integral says if you're doing a vector line integral of a gradient, you can compute that as f of b minus f of a. Likewise, for the blue integral, I'm doing a vector line integral of a gradient, and fundamental theorem of line integrals says that's f of b minus f of a. And because these two curves, and again, very important, they start at the same point, they end at the same point. That means that f of b minus f of a is the same for both of these line integrals. And that means that the integrals themselves are equal. And that means that our vector field, our gradient vector field, has to be path independent. Everybody on board with that? So Okay. Questions? Feel free. Okay, so regularity concerns. So let me just say, look, there are various places along in here where there are regularity concerns. I'll recognize that they're written down, and I'll probably say it once or so, perhaps. But it's very tedious to have to repeat it over and over again. So I'm mostly going to just say gradients are path independent by this argument. And it turns out also to go the other way, path independent, again, we've got to worry about regularity issues, but path independent vector fields also are gradients. This is a little bit more trouble to prove. If you want to see a quick sketch, this will get you started. You don't have to do this. This is one of the, I forgot to label this, but think of this as being labeled as optional, but helpful if you're interested. So anyway, if you're curious, feel free to look at that. You don't have to. So, regularity issues aside, path independent is exactly the gradient fields. Okay. All right. Moving along. Here's a different way to say it. Same punchline, but kind of rolls off the tongue a little bit differently. Again, shared starting point, shared ending point. One curve like so, another curve like so. So different curves, same starting point, same ending point. And let me remind you that path independence means that the C1 integral and the C2 integral will always be the same. So let me read. Oh yeah, question. Yeah, go ahead.
So the orientations are different. You're just adding up those.
Oh, that's I totally hear where you're coming from, and it feels like they're different. But it also, in a certain way, kind of feels like they're the same. They both start at the same place. They're going to the same final point, right? It doesn't. I mean, if this was the route that I drove and this was the route that you drove, I mean, we would kind of, in some sense, feel like we're going the same way. You know what I mean? But I totally hear what you're saying as well. Green is going counterclockwise, blue is going clockwise, and in that sense, they feel different. Great point that you're touching on, and what I think the right answer to this question is neither. You can't compare those orientations. The reason you can't compare those orientations is they're different curves. Right? So the idea of two different orientations makes sense if you're talking about a single curve, right? So if there is a single curve, then you can talk about, that orientation versus that orientation on that single curve, right? But if I look at that curve and this curve, and I say I'd like to compare that orientation with this orientation, that doesn't make any sense. You see what I'm saying? Right? So it is alluring to think of this as same and either same or opposite orientations, but it just doesn't make any sense any more than this does. Is that cool? Okay, yeah. So we want to try to shy away from the phrasing of green and blue being oriented the same or oriented different. I want to say instead they have the same starting point, they have the same ending point. Yeah. Is everybody happy with that? It's a very subtle point, but worth thinking about. Okay, right, back into it. Path independence means green equals blue. How else could I say that? Well, I could say that green minus blue is 0. Same means their difference is 0. Now let me say that a little bit differently. I'm going to think of this as moving along a single path. I start off on C1. Now note the positive sign here, so I'm going along C1 in the direction that C1 goes. And then C2, well, no, wait a minute, with a minus sign, this minus sign means what I actually want to do is go backwards along C2. Right now, C2 goes this way, but minus C2 going backwards means I'm going to go the other way. And now I don't want my picture to not look good at the end, so let me sort of redraw. Like that. Is that cool? Okay. So another way to say that these two line integrals have to be equal. In other words, another way to say path independence is that I need all of these orange kinds of integrals to be 0. Oh, wait. We have a term for these kinds of integrals. Right? When you have a vector line integral over a closed curve, we have this pre-existing term circulation. Right? So that's the alternative phrasing for path independence. Circulations must all be 0. Everybody happy with that? All right. So, and that's what I've written here. Circulations, right? Line integrals on closed curves are all 0. Okay. And I'll go ahead and just for the sake of consistency, yeah. Okay. Now, here is a take on that, and this is just for fun, and don't worry about it, but I do think this is a fun example. Are you all familiar with this artist named M.C. Escher? If you're not, he's a fun artist. He likes kind of visual illusions and visual contradictions, things that you can do in art that you can't do in the physical world. That kind of thing. And he does a lot of different things. Did. And this is one of his famous drawings. And I have to admit, I don't know what the medium is. Not my area. Oh my, what just happened here? Okay, we're back. I hope the recording is still going. Fingers crossed. Okay. What's going on here? Well, the weird thing about this, and again, you may have seen this before, but if you look at these people here, right, we've had these people climbing the stairs, and if you look at the people going along the outside, well, they're going up. You can see they're going up the stairs there, and then you sort of follow them along. Well, that's up. And then along those guys there, they're going up, and then they continue to go up. But wait a second, they just got right back where they had been. How's that possible? They were going uphill the whole time, and they got right back to where they were? What? Right? Doesn't make any sense. It's non-physical. Right? And then likewise, you can look at this other sort of group here, and these folks are going downhill, and then more downhill, and then more downhill, and then more downhill, and got right back to where they were in the first place. Again, that's complete nonsense. It's non-physical. So you can draw it this way because you can lie with drawing. It's the short version. But so it makes this sort of optical illusion. Okay, does everybody see the idea there? Okay. So for whatever it's worth, this observation that we just made about gradients and path independence and circulations having to be 0 is kind of a mathematical take on why this is a picture of nonsense. So if you think about it, let's consider let's let h be the altitude function. Right, so h says wherever whatever your x and y are, h is your altitude. How far above sea level are you? Or let's say here, how far above the ground are you? Right? And well, we know that the gradient of that is a gradient, and we further know that gradient, that's the thing that when you dot with dr, will keep track of how much your altitude is changing. This is delta h. Or I guess we'd say DH right there, right? Gradient dot input change gives you output change. That is ultimately just a chapter 2 reference there. So let's think it through then. Well, this is a gradient. If it's a gradient, it's path independent. If it's path independent, as we just saw, that line integral, that closed line integral, has to be 0. Going all the way around, it's got to be 0. So the suggestion of the drawing. Now let's look at what does the drawing say? The drawing seems to suggest that we're gaining altitude every step we take as we go along the outside. All those DHs are being drawn as if they're positive. The drawing would have you believe that this line integral is positive. But of course, path independence tells us it has to be 0. So anyway, now, does this prove anything useful? Nonsense. No, of course not. This is perfectly obvious, casual glance, right? Many non-mathematicians have looked and instantly seen the contradiction in this image. You don't need the math to be able to see that this is a picture of nonsense. This is just a phrasing of sort of a mathematical take on what, again, is visually, I think, intuitively pretty obvious. Another way to say this is that this piece of art is, let's see how to say this, the nonsensicalness of this piece of art is a take on why this really should be true for path-independent vector fields, right? What I have in purple, if it weren't true, would suggest that this nonsense is possible, which is clearly nonsense. So anyway, feel free to, I would encourage you all to think about this as kind of a nice point of view on why this makes sense. Everybody good with that? All right. Okay. Now, what is this good for? And I'm going to say that it's more useful conceptually than it is computationally. But there's pros and cons to that statement. Let me tell you why this is useful conceptually, and I'm going to go back to physics again. So, I briefly, some time ago, whenever that was, might have been Friday, was talking about how we call certain vector fields conservative because they allow for this idea of a conservation of energy. And in particular, what a conservative vector field is a vector field that allows for an associated notion of potential energy. Now, if you think about it, potential energy needs to make sense depending only on location. Right? If I say that, look, I walked into this building at the front entrance, and now I'm standing here, and I have gained a certain amount of potential energy by the fact that I got myself to this spot, right? The front entrance is way over there and downstairs, and so I've gained some potential energy. It wouldn't make any sense for me to say, well, but how much potential energy depends on whether I came up this stairwell or whether I came up the other stairwell, or maybe I went around the sort of the loop of the building, and none of that should matter, right? If we're going to talk about potential energy as depending on location only, the path can't matter. The force field has to be path independent. Right, so path independence is directly connected to the idea of potential energy, which means it's directly connected to the idea of conservation of energy. Right, so that's a conceptual argument that we can make with path independence, and that's very nice and I think very valuable. Whereas, let's think about the computational use of path independence. Just real quick. Computationally, if it's path independent, well, that means it's a gradient. Wait a second. If it's a gradient, I could just use the fundamental theorem of line integrals. Fundamental theorem of line integrals is a sledgehammer for computations. We'd have to beat minus f of a, but we don't need help with that in most cases. Right? So computationally, who cares? Right? How is having an alternative to the fundamental theorem of line integrals really all that helpful? And that's largely true. But here's the one, I'm just going to make the observation. There are some cases where even though it is perfectly clear that a vector field is a gradient, it might actually still be hard to find the anti-gradient, which I would need to do the computation. So there are some such cases. The one I'm about to show you is not one of those cases. Cases where finding the anti-gradient is hard require really hard vector fields, and I don't want to deal with a bunch of algebraic horrors that are not really the point. So let me just say in this example that follows, we're going to ignore the fact that, this vector field here, once I know it's path independent, I know it's a gradient, I know there's an anti-gradient. Now I'll bet you if you were to play little clever games, you'd probably be able to dream up what the anti-gradient is. Right? It'd be a fun little exercise. Let's see if you can, smart alecky, can you dream up an anti-gradient that would work for this? And I'll show you how later. So we're going to pretend that we can't. We're going to pretend that we don't know how to do an anti-gradient. We're going to pretend we can't use the fundamental theorem of line integrals. And path independence is nice in a case like this. So in particular, let's see, our curve, top half of the unit circle oriented clockwise, our curve is like this. Keep in mind we are given that this vector field is path independent. We're given that it's path independent. By the way, how did I know that this was path independent? I'll show you in a minute. But for the moment, we know it's path independent. It's given that it's path independent. Let's capitalize on this. Hey, if it's path independent, I can choose any other curve that I like. Right? Any curve that I like that starts at the same point. Remember, very important. Path independence only works if the two curves start at the same point and end at the same point. So I've got a huge number of options. I could pick that path as my second path. I could pick that path. I could do a couple of loop-de-loops over there. Whatever I want to do. What path am I going to pick? Look, I'm lazy, right? I want to make my life as easy as possible. I'm going to pick the easiest seeming path that I can, and I'm going to pick that path right there, since I'm free to pick whatever I want. Okay, is that cool so far? So, amazingly then, because I'm given this path independence, I no longer have to worry about the blue curve. Forget about the blue curve. Never liked that curve. It's curved. It's going to bring up trig, right? It's going to be a pain. This green curve is so much nicer. This green curve, super easy to parameterize. Effortless to parameterize. And look how the integral breaks down. The integral breaks down pretty great in a couple of different ways. For one thing, notice, because y is always 0, right? My new curve, it says right here, y is always 0. Well, that allows me to rewrite that as that. If y is 0, then 2xy is also always 0. And here's another thing. If y is always 0, that means that let's see, how am I going to say this? The dr vector that would go like, let's say like this, dy will be 0, right? I'm moving horizontally. That means there is no upward component to it. That means that my dy is 0. And as a result of that, my f dot dr, I can just explicitly see my f dot dr, that dot product, clearly 0. The integral is therefore 0. This integral fell apart into nothing just because I used the path independence. How we doing? All right? All right. So there are a few such situations. By the way, if you want to see a better example, something that's a little bit more persuasive, right? I mean, you're probably thinking, you know what, this is a silly example. I can just find the anti-gradient. It's not that bad. Look through my older exams, way back when, 15 years ago. I dreamed up some wacky vector fields that are gradients. But we're finding the anti-gradient is intractable. Right? And then the question was to compute the vector field, and something along these lines was the only feasible solution. So again, you look through my old exams, and you'll find some. Okay, moving along. Okay, so how do you know? Right, let me go back real quick. We were looking at this example here, and how did I know that this vector field was a gradient of something? I just sort of knew somehow, right? How do you know? So here's a good answer to that question. It's what we're going to call a local test. I have 5 statements here that I claim are all equivalent for an appropriately nice, appropriately regular. We don't want to worry about those kinds of problems. We already know that these 3 statements are equivalent. Regularity issues aside, right? Every gradient is path independent. Path independent means that closed line integrals are 0, namely circulations are 0. And I'm going to say these other 2 statements are clearly equivalent to each other, because if you've got a function, never mind the fact that it's a curl of something, it's not the point. If you have some function that's equal to 0, well, of course all of its integrals are 0. And also, if you have some function where all of its integrals are always 0, no matter what domain you pick, all of those integrals are 0? How could all of the integrals of something possibly be 0? The function itself must be 0. So I'm going to say we've established that the green 3 statements are clearly equivalent. I'm making the case here that I think these 2 blue statements are clearly equivalent. And I claim now that they're connected to each other because Green's theorem tells us that closed line integrals can be computed with double integrals over the interior. Is that cool? And this gives us what we're going to call our local test. So, the local test is that if you're trying to decide if something is trying to decide if something's a gradient, aka if you're trying to decide if something is path independent, compute the curl. That's something you can compute locally. That's not a global construction. Whether a vector field is a gradient, the vector field everywhere has to be the gradient of the same single function, right? That's not what we're doing here. I'm just saying, just compute the curl. You can compute curl locally. And just make sure that it's 0 everywhere. And if it is, right, if you compute the curl and if you get 0, then you can immediately conclude, yes, your vector field is a gradient, and yes, your vector field is path independent. It's a really nice little test. Everybody okay with that? By the way, I have another take on this that I really like. Again, we have these 3 statements. We have these 2 statements. How do we connect the green to the blue? This one's just rolls off the tongue so nicely. If circulations are all 0, if there's no circulation, then there's no circulation density. How about that? Crisp, right? Immediate. No circulation, no circulation density. Gets us right on it. So I think that's fabulous for intuition, and you might say for sort of memory purposes, right? And I hope you'll find that useful. Anyway, it's just another point of view. By the way, a little bit of terminology. How do we describe the feature of a vector field having its curl equal to 0? Well, don't forget that curl, we've already talked about an intuition for curl. Curl describes the extent to which there is a rotational element to the vector field. If the vector field is, you drop the little leaves in the water and they'll rotate as they float downstream. So curl measures rotation. So if there is no curl, then there is no rotational aspect to the fluid, and so this test, also sometimes called irrotational. So you'll see that sometimes, and it's good to be heads up on the terminology. Sometimes vector fields are described as irrotational, and so it's important to be able to recognize that when you see irrotational, that means curl is 0, which, by the way, also means that it's a gradient, which, by the way, also means that it's path independent. So, for your consideration, for your sort of studying and planning purposes, all three of these terms, irrotational, gradient, and path independent, they're all talking about different features of the exact same vector fields. Again, regularity issues aside, I don't want to worry about that, right? Aside from regularity problems, and by the way, that nasty things come up. If you take away the C1 requirement, if you allow singularities, then all of a sudden these are not quite the same, and it's a fascinating little exploration of which happened when in which cases, but it's not what we want to focus on in this course. So regularity issues aside, if you see irrotational, you instantly know it's path independent. You instantly know it's a gradient or something. And by the way, don't forget, we also have another terminology for gradients, conservative. So we have 4 words to be on the lookout for, right? 4 words. If you see any one of those 4 words, you also get the other 3. Everybody happy? Okay. All right. Yeah.
So that proving would be a vector field is conservative?
Yep. That's right. Yeah, so all 4 of these words describe vector fields. Absolutely. Okay. All right, now real quick, this theorem that we just stated here is a statement about vector fields in R2. There is an analogous statement in R3. And let's see here. Let me highlight this differently. Analogous statement in R3, and again, it's curl, as it turns out. Now, it's a different world, and there's different considerations, and how I got to this is going to involve a different argument. And hey, wait a minute, the critical step that we took right here, right, involved using Green's theorem. I would need to have sort of a 3-dimensional version of Green's theorem to be able to make, the analogous argument down here. Wait a minute, we don't have a 3-dimensional version of Green's theorem yet. But we will very soon. And once we have that 3-dimensional version of Green's theorem, then we will be able to complete this argument. So I'm going to give you the result here in advance so that we can use it, for kind of, getting stuff done. But we'll be able to complete this argument once we have that analogous theorem. Okay. So let's actually use these. A couple of examples. Here's a vector field. Is that a gradient? At a quick glance, it's pretty hard to tell, right? Unless you're just blazing fast with algebra, which I'm not. It's just not immediately clear whether there is an anti-gradient for this vector field. Should I go looking for an anti-gradient? Well, golly, if I go off and start looking for an anti-gradient, and I'm going to show you all how to do that in just a couple seconds here. But if I do, if I can't find it, does that mean there isn't one? Or maybe that just means I'm bad at this? How do we know? Right? So it's very nice to have a crisp, immediate answer to the question of whether something is a gradient. And again, we have this theorem right here. If you want to know whether something's a gradient, right, that's the question that we're asking. Is it a gradient? Okie dokie, we'll just compute the curl, see if it's 0. Question resolved. And so fine, so we do so here. Let's see here. Here we're going to compute the curl. and I'm going to start computing it. Now do keep in mind, by the way, the curl in 3 dimensions, curl of a vector field is another vector field. And I would need it to be 0. And wait a second, as I started computing this curl, here was my first coordinate of the curl, and I claim we're done. It's already revealed itself not to be 0. Right? I mean, it doesn't really matter what these second and third coordinates end up being. Even if they were both 0, this is already not 0. My vector field is not the 0 vector field. We're done here. What do you think? Is everybody okay with that? It's a clever little insight. And it'll save you a little bit of computation. Right? Now, had we gotten 0 for the first coordinate, you still go either way with the second and the third coordinates. And so if you keep getting 0, you do have to keep going. You might get all zeros. You might not. Then it's not clear. But when you get a non-zero, you're done. Okay. Here's another example. Here's a 2-dimensional vector field. Is that a gradient? And again, you can play algebraic games, and again, you're going to find yourself grappling with this ugly question of, well, maybe there is no anti-gradient, or maybe I'm bad at this and I don't know how to find it. My own personal failure to find something does not mean that it doesn't exist. Right? If that were the case, then my car keys just straight up don't exist sometimes. That's not how it works, right? That's just not reality. So, okay, well, let's use our tool. The tool up here is that this is resolved by computing the curl and seeing if you get 0 or don't get 0. And I can compute the curl by the usual formula. It's not 0. We're done. No anti-gradient. Don't waste your time trying to find it. There is none to find. Everybody happy? Now, by the way, just a little personal satisfaction can be found by reminding yourself that this vector field looks like this, and then remind yourself also that, well, wait a second, if this were a gradient, then it would also be path independent, which means also that all the circulations would have to be 0. That clearly is not what we're looking at here. Clearly, if I go counterclockwise, I get a positive circulation. In fact, and as I point out in what I wrote over there, this is kind of reminiscent of the Escher stairs, right? If these vectors really did all point uphill, if it were a gradient, this would be the Escher stairs all over again. Everybody happy with that? So I'm going to call this a satisfying justification of what we already computed. Okay, so let's see. We've got 2 minutes left. Let me just say a couple of really quick things. We talked previously about this business. I made this statement back in chapter 3. We had already talked about gradient, of course, and then in chapter 3 we introduced 2-dimensional curl. And I made this statement that when you compose them like so in this order, that there's something fundamentally natural about that and that good things happen. And we've already seen some of these results. We know that this is, I may or may not have used the term exact sequence, but if you move 2 steps, you get 0. And lifetimes are always 2 and all that business. So I just want to point out another cool thing that has happened as a result of this. Now, I'm going to make the observation that this really is pretty natural. The idea that if I have a 2-dimensional region and if I look at its boundary, well, I'm going to get a curve. And if I take a curve and if I look at its boundary, I'm going to get a couple of points. So, okay, so this, what I have in blue, is very natural. That's just how boundaries work. And now check this out. These players right here all pertain to the fundamental theorem of line integrals that we were just talking about. It's a statement about a curve and its boundary points. It's a statement about a function and its gradient field. How about that? Right? And then these players are all involved with Green's theorem. Green's theorem is a statement about a two-dimensional region and its boundary curve. And also is a statement about a vector field and its curl function. So there's kind of a naturality there that, putting these in that order dovetails very nicely with the, of course we're going to put these in this order, pieces kind of start to fit together. Okay, and there's other really cool things about this, the wonderful coincidences that have sort of already started to appear, and we'll pick up here next time. Y'all have a good rest of your Monday. See you later.